Hello learners, in this program I will discuss about the Exsolution intergrowth. What is Exsolution intergrowth? Exsolution intergrowth is the process of releasing excess volatiles from an oversaturated melt. Exsolution intergrowth is attributed to the release of excess of volatile from an oversaturated melt, and as a result sudden dumping of cations is taking place and Exsolution intergrowth has taken place. I am citing an example of pyroxenes, magnetite ulvolospinel solid solutions and alkali feldspar when crystallized in slowly cooled magma as a homogeneous minerals from the melt exsoled at subsolidus temperatures. See carefully, when the magma contains excess amount of volatiles and it crystallizes under subsolidus temperature. I will let you know what is subsolidus temperature in my next PPT. The Exsolution phenomena takes place. As a result, stable coexisting crystalline phases are formed. Exsolution texture is represented or commonly known as perthitic texture. The rock is called perthite, an intergrowth of Na and K rich alkali feldspar by unmixing below alkali feldspar solvus. This subsolidus and solvus I will show you in my next PPT. Very interesting, this is again an example from the Eastern Deccan lava flow, where this is a very high magnification photograph. It can't be seen under the normal petrological microscope under low magnification around 100x, it can't be seen, but it can be seen under very high magnification, must be 20,000 or 40,000. I am not able to show you the exact magnification because of certain technical limitations, but it is very high magnification photograph. And this scanning electron microphotograph showing A means this photograph shows cube shape, this is a cube shape magnetite crystal, triangular shape magnetite crystal, again in B photograph triangular magnetite crystal. C, this is prismatic magnetite crystals, and D, elongated chain like anhedral grains, is like a bead like structure and it is in the form of a elongated chain like anhedral grains. All the grains are anhedral magnetite grains, or sometimes they are reniform. Reniform means they are similar to the kidney shape. They are kidney shaped grains, they are present there of magnetite. All these varieties, cube shape, triangular, prismatic, reniform, chain like, all varieties of grains, they can be seen or they are formed by Exsolution between magnetite and ilmenite. Here in this slide, this magnetite, remember this is in Exsolution with the ulvospinel, ilmenite and hematite minerals. Ilmenite 1,0,1 lamellae exsoled from the remaining cube. See here the 1,0,0 lamellae, this is a lamellae, this lamellae is exsoled from the melt, remaining melt, and this is a cube shaped magnetite. This 1,0,0 lamellae exsoled from the remaining cube shaped magnetite. Irregular projections of magnetite and ilmenite are due to unmixing of the two mineral components. Ilmenite lamellae vary in size and lie parallel to 1,1,1 plane. These lamellae, they lie parallel to 1,1 plane of the magnetite. Finger shaped residual areas are formed by replacement of magnetite. So, these important features, they are all textural features, they tell us very interesting story about the what has happened in the past, how the rock has been crystallized, how it has been formed, they can be easily ascertained by these textures. Now, I am coming to another variety of texture which is called perthites and antiperthite or perthitic or antiperthitic textures. What is perthites and antiperthite? Perthites, they are mixtures of two alkali feldspars where host, always the most abundant phase, we call it as host, is relatively orthoclase rich. OR means orthoclase rich, and guest is relatively albite rich, is termed as perthite. When you have a host of orthoclase and guest mineral is albite, we call it as perthite. This is a normal situation, but in certain cases situation is reversed. When the host is albite rich and guest is orthoclase rich, such alkali feldspars are called antiperthite. But this perthite and antiperthite relationships are discussed on the basis of size and shape of the guest phase, and they can be further categorized into three major categories such as macroperthite. Macroperthite, when guest phase is coarse grained and it can be seen by naked eyes or with unaided eyes without the help of microscope or without the help of a hand lens, you can see such kind of perthitic relationship or antiperthitic relationship, then the rock is called macroperthite or the texture is called macroperthite. Two phases can be seen with unaided eyes. Microperthite involves application or use of polarizing microscope is required to see or to distinguish two phases, which one is host, which one is guest, which one is orthoclase, which one is albite. If these two phases can be seen under the microscope, the texture is called microperthite. Cryptoperthite, when these two phases can be distinguished by X-ray diffraction techniques, X-ray diffraction analysis that reveals such kind of texture, then we call it as cryptoperthite. Ultra fine grained crystals, they cannot be seen by under the microscope, but that can be distinguished with the help of X-ray diffraction patterns. See, in this thin section, this photograph, this is directly taken from the microscope and it represents complete solid solution and orthoclase albite eutectic system. Orthoclase and albite, they are in the eutectic relationship. Normally albite and orthoclase, they are in a solid solution, but here they are in the eutectic relationship. With solvus, it involves separation of two solid phases from a homogeneous solid solution. Two solid phases, that means this is the perthite here, these two perthites, they are exsolved from the other mineral phases caused by difference in the size. These are exsolved because of the difference in the size. What is seen here? Feature is more or less same, but what is the difference? The feldspar is myrmecatized. The legend, SiO4 legend, is detached from the cations and it is present here in the form of a vermicular quartz, which shows myrmecatic texture. So, again difference in the size of K ions, K means potassium ions, their ionic radii is 1.59 angstrom, whereas sodium cations, they have ionic radii of 1.24 angstrom. So, their ionic size is not much difference in their ionic radii. So, they can be replaced, Na can replace potassium, potassium can replace sodium, vice versa. This replacement is possible. As a result, orthoclase and K feldspar rich, or see here the orthoclase feldspar here, both of them, the Na ions, they can be replaced by K ions. As a result, you get perthitic texture, but this perthitic texture is because of the reason that the cation Na and K have more or less similar ionic radii. If there is a vast difference in ionic radii, such kind of replacement will not take place and you may not get a perthite or antiperthitic textures here. When bulk composition is K rich, here lamellae of Na rich feldspar form in K rich host, then perthitic texture will form. This graph here, you see here, This indicates crystallization between the two end members of the feldspar. What are those end members? Orthoclase and albite. And here this is a solidus, this is a liquidus curve. Here in this case also you have a liquidus curve, you have a solidus curve, and in between these two curves are, this is actually a phase diagram, and in this phase, in this area, only K rich feldspar plus liquid they can exist. Here in this area, albite rich feldspar plus liquid will exist here. Now, what is happening? Suppose a crystal is crystallized somewhere here, that means above solvus temperature, as I have told you in previous slides. As a result, perthitic texture will be developed, and reverse is the case when antiperthite is developed. So, these are the crystallization of two feldspars that is taking place, and that represents the way how the two end members they behave differentially. As a result, perthite and antiperthite textures have been formed. One is formed above solvus temperature, the other one is formed sub solvus temperature. So, that gives rise to such kind of textures. What is antiperthitization of plagioclase by microcline? Here you have a plagioclase crystal. This large plagioclase crystal, it shows lamellar twinning, and this M written here, this is because of antiperthitization. Antiperthitization is again alteration of plagioclase is taking place. This irregular zone, again in this area, this here you see again plagioclase crystal is there, but in between this you have a gray color M. M, this is an antiperthite. Antiperthite means you have a different host here. So, this shows antiperthitic relationship here. Learners, let us summarize what we have learned. We have learnt about Exsolution intergrowth. Thank you very much.